Have you ever gazed at the night sky and wondered if what you see is truly real? What if our entire universe is just a projection, a hologram encoded on a distant two-dimensional surface? This isn't science fiction. It's a radical idea from the frontiers of theoretical physics, the holographic principle. It challenges our deepest assumptions, suggesting that the space and volume we perceive might be an illusion. Are we living inside a cosmic projection? Is information, not matter, the true foundation of our universe? In this video, we'll dive into 10 fascinating concepts that underpin the idea of a holographic universe, from black holes to string theory. Buckle up and get ready to have your reality questioned. Let's start with the holographic principle itself. Imagine a credit card's hologram, a flat surface encoding a 3D image. Now, scale that up to the universe. The principle, proposed by Gerard T. Hooft and Leonard Susskind, suggests that everything inside a region of space, galaxies, stars, you and me, can be described by information stored on its boundary. Our three-dimensional reality could be a projection from a two-dimensional surface. This flips our intuition. Information isn't packed into volume but limited by surface area. Like the universe's maximum pixel density, it's not just a thought experiment. It addresses deep paradoxes in physics, especially around black holes and the quest to unite gravity with quantum mechanics. If we want to understand the universe's fundamental laws, we may need to look at the two-dimensional screen, not the three-dimensional world we experience. The holographic principle is the foundation for everything we'll explore next. It's a radical shift, but it's grounded in real physics. So how did this idea emerge? Let's find out. The roots of the holographic principle lie in string theory, an ambitious attempt to unify all forces of nature. String theory proposes that the universe's fundamental building blocks are tiny, vibrating strings, not point-like particles. For the math to work, string theory needs extra dimensions, up to 10 or 11. The breakthrough came when physicists discovered that a universe with gravity in higher dimensions could be fully described by a simpler, non-gravitational theory on its lower dimensional boundary. This duality, first made concrete by Juan Maldacena, gave the holographic principle real mathematical footing. Suddenly, the idea wasn't just philosophy, it was a tool for calculations. String theory's complex landscape became the perfect lab to explore how our 3D universe might emerge from a 2D reality. This connection between volume and boundary is at the heart of the holographic universe. Black holes are where the holographic principle truly shines. According to quantum mechanics, information can't be destroyed. But Stephen Hawking showed that black holes evaporate, seemingly erasing information forever. A paradox. The solution? Maybe the information never enters the black hole's interior. Instead, it's encoded on the event horizon, the black hole's two-dimensional surface. As the black hole evaporates, the information is released back into the universe, scrambled but not lost. This idea inspired the holographic principle. If all the information in a black hole is stored on its surface, could the same be true for the entire universe? The paradox forced physicists to rethink the nature of space, information, and reality itself. The event horizon acts like a cosmic hard drive, storing every bit of data that falls in. The black hole's surface, not its volume, holds the key. This was the spark that ignited the holographic revolution. If it works for black holes, why not for the cosmos? The holy grail of physics is a theory of quantum gravity, one framework to describe everything from subatomic particles to galaxies. General relativity and quantum mechanics don't mesh, especially in extreme environments like black holes or the Big Bang. The holographic principle offers a new approach. Maybe quantum gravity in 3 dimensions is secretly equivalent to a simpler, non-gravitational theory in 2 dimensions. This could make the hardest problems in physics solvable by translating them into a lower dimensional language. Instead of quantizing space and time, we might only need to understand how our 3D world emerges from a 2D quantum system. Gravity and space-time could be emergent phenomena, not fundamental. The holographic principle isn't just a curiosity. It's a guiding light in the search for quantum gravity. It suggests that one of our dimensions might be a projection from a simpler reality. The most concrete realization of the holographic principle is the ADAS-CFT correspondence, proposed by Juan Maldacena. In this duality, a theory of gravity in a 5-dimensional anti-de Sitter space is mathematically equivalent to a quantum field theory without gravity on its 4-dimensional boundary. Every object and interaction in the ADAS bulk has a counterpart on the boundary. This duality is powerful. Hard problems in gravity become easy in the boundary theory, and vice versa. While our universe isn't EDS, this correspondence proves that holographic duality can be precise and calculable. It's a theoretical lab for studying quantum gravity. The ADS-CFT correspondence is the strongest evidence yet that a holographic description of reality is possible. It shows that the universe might be fundamentally two-dimensional at its core. The boundary encodes the bulk. This is the dictionary physicists use to translate between worlds. Entropy, the measure of disorder or information, turns out to be crucial for the holographic principle. Normally we think entropy scales with volume, but black holes break this rule. Their entropy is proportional to the area of their event horizon, not their volume. This was the Bekenstein-Hawking discovery, and it suggested that all the information about a black hole is stored on its surface. The Bekenstein bound says there's a universal limit to how much information can fit in a region set by its surface area. If you try to cram in more, you get a black hole. This is the bedrock of the holographic principle. The universe's information content is limited by its boundary, not its bulk. Our 3D world could be a projection from a 2D cosmic screen. Black hole entropy forces us to take this idea seriously. Physics used to be about matter and energy. Now information is taking center stage. John Wheeler's it from bit idea suggests that every particle, field and force arises from information. The universe is like a cosmic computer and the laws of physics are its code. The holographic principle is the ultimate it from bit. If our universe is a projection of information on a 2D surface, then information isn't just a description, it's the reality itself. The fabric of space-time might be woven from quantum information or qubits. This shift changes the questions we ask, not what is the universe made of, but how is it computed? Physics and computer science are converging, and the universe might be the ultimate quantum computer. Information is the new foundation of reality. Is there any evidence for a holographic universe? Direct tests are tough. The relevant scales are far beyond current technology. But there are hints. Some features of the cosmic microwave background fit simple holographic models as well as standard cosmology. Experiments like Fermilab's holometer searched for holographic noise, tiny jitters in spacetime, but found no definitive signal. Still, the search is young and the evidence is subtle. The fact that holographic models are consistent with large-scale data keeps the idea alive. Physicists are designing new experiments to probe the limits of space and information. Even a whisper of holographic noise would revolutionize science. For now, the principle remains a bold, testable idea. The holographic principle doesn't just change physics, it transforms philosophy. It challenges reductionism. Maybe the universe can't be understood by breaking it into smaller parts, but by looking at its boundary. Locality and causality blur. Two distant points in 3D space could be neighbors on the 2D surface. This could explain quantum entanglement, spooky action at a distance, as a feature of the holographic map. What about consciousness? Are we just projections, or do we help read out the hologram? The line between observer and observed, reality and simulation becomes fuzzy. Ancient philosophy spoke of the world as illusion. The holographic principle echoes this in scientific language. The universe may be more interconnected and mysterious than we ever imagined. Our solid world could be the grandest illusion. The implications will ripple through science and philosophy for generations. So what does it mean if our universe is a hologram? It's a paradigm shift. Our 3 dimensions might be emergent, not fundamental. Reality would be a projection from a cosmic hard drive, a 2-dimensional surface, but our experiences are still real. The underlying nature is just stranger than we thought. This perspective could help unify physics, translating impossible problems into solvable ones. It connects us to the cosmos. We're not just in the universe. We are the universe, experiencing itself. The holographic principle invites us to embrace wonder and keep questioning. Whether proven true or not, it forever changes how we see reality. We've explored the idea that our universe might be a grand illusion, a hologram projected from a distant surface. What do you think? Does the holographic universe resonate with you, or is it a step too far? Share your thoughts and questions in the comments. If you enjoyed this journey, subscribe for more mind-bending science. Thanks for watching. Keep questioning and keep looking up. If you enjoyed this video, don't forget to subscribe, like and comment below. Your support helps us bring more mind-bending science to you. Hit that subscribe button, give us a thumbs up, and share your thoughts. Every click counts. Thank you for being part of our curious community. See you in the next video.